Okay, so hi everybody. We're very pleased to announce that this week's seminar will be given by Alex Townsend. Alex is an associate professor at Cornell University. His research area is in numerical analysis, scientific computing, and theoretical aspects of deep learning. Alex has won numerous awards for his research. Recently, he won the Career Award in 2021. So today he will be talking about learning Green's functions associated with elliptic PDEs and parabolic PDEs. So the floor is yours, Alex.
Okay, yeah, thank you very much for the introduction and the invitation. So today I'm going to be speaking about one topic in, let's say, scientific machine learning. So as you guys know, scientific machine learning is maybe an emerging field in machine learning and data science, where you try to do some machine learning techniques to do some science, to help science. And one of those fields inside scientific machine learning is PDE learning, where you try to take system responses from PDEs when you force them and try to uncover something about the underlying differential equation. So today I'm going to be talking about PDE learning, and I'm going to try to uncover, the thing I'm trying to uncover from the PDE is, I'm not going for the full PDE operator, I'm going to go for what's called the Green's function, which is, as I'm going to show you, is maybe a way to get rigorous tools into PDE learning. So this is joint work mainly with Nicholas Boole, who's a PhD student, who was a PhD student, he just graduated, now he's a postdoc at Cambridge, along with four other people that have helped shape our ideas. So, so the question that we're trying to ask, or the field of PDE learning is trying to ask, is can you learn an unknown partial differential equation from input-output data? So you imagine that there's an underlying partial differential equation. You get to force the system. These are the FJs. So in classic PDEs, this will be like the right-hand side of the PDE. And you get to witness back the solutions UJ. So you could imagine that there's some kind of solution operator, right inverse of the PDE, that takes you from the right-hand side, the forcing, the systems that you're forcing with F, to the system's response, which is the UJs. Okay, and people often try to go and try to learn this right inverse of the PDE, which is a solution operator, which takes you from right-hand sides to the solution. And so this is the kind of data that you might collect. So you get to choose the FJs. This is how you force the experiment or the PDE. And you get to witness the UJs. So you collect up these input-output data. FJ here, as I'm just imagining, is a function, though usually in practice it's discretized. And UJ, I'm imagining here, is a function, though of course in practice it's discretized. And you know that it comes from the solution to a partial differential equation. And your goal is to try to uncover something about this operator L. Here I'm imagining that I'm just trying to put it in the simplest situation so I can do some theoretical work. I just imagine that I'm on some domain omega and I have Dirichlet boundary conditions. These can also be, G can also be part of the inputs in some cases. For the theory, because my goal is to be inspired by the techniques that are being used in neural nets and to try to make or construct a fully rigorous algorithm that uncovers this Green's function associated to a PDE. And so to do that fully rigorously, I'm going to have to restrict my class of PDEs that I consider and consider PDEs class by class. And one of the simplest classes that I can demonstrate this theory in is the collection of self-adjoint, so this is essentially symmetric, second order elliptic PDEs. These are linear PDEs with Dirichlet boundary conditions. And what I'm going for is I'm going to tell you how many input outputs you need to recover this Green's function associated to these PDEs to within your chosen accuracy epsilon. So I'm going to try to be fully rigorous and give you everything you need to know about how much input output data you need. So of course there's lots of practical work here. And that's where our work is inspired. We were watching these people learn this solution operator and trying to understand why is it even possible to do such a thing, and then trying to prove that it's possible, and then what's the rate that you might be able to get in terms of input output data when you try to learn this solution operator. So there's many approaches to learning this solution operator. This is like the right inverse that takes you from F's to U's, and this is somehow more useful for theoretical study than learning the PD operator itself, because the PD operator, even for this second order elliptic problem, is an unbounded operator. And this makes it tricky to make learning precise, whereas this solution operator can be compact. So this is a more useful functional analysis setting to be in. So this is what people do in practice. They take their F's and U's, these are the pairs, the forcing terms and the solutions, and they train a neural net which takes in F's, well, usually they're sampled on a grid, and outputs the UJs sampled on a grid. And that would be this a neural net that's trained to predict what this solution operator is doing. And we like it a lot because the solution operators, once they've been trained, are really fast to evaluate. So this means if you give me a new right-hand side, I can predict what the response, the UJs, will be if you give me a new one after training. And then, of course, people play with the neural network architecture inspired by numerical PDEs techniques to come up with different architectures to represent this solution operator in. So maybe a nice one is this Fourier neural operator technique, where maybe inspired by Fourier spectral methods, they have a kind of a transform which is motivated by Fourier transforms, an inverse Fourier transform, and a neural net sitting in between that they're using to train this solution operator with. And this is a nice approach because it learns a family of solution operators that are parameterized. So anyway, there are lots of different techniques, and we're trying to ask the mathematical questions here. So what are the mathematical questions? They're always along the lines of, what type and number of training data do you need? So how much input output data do you need? Do you have any performance guarantees? What's the right neural network architecture, and can you deal with noise? And so I'm going to develop an algorithm where I can answer these questions. And once you've discovered this solution operator, a lot of the neural net approaches, they're good at prediction, like predicting a new f, a new u given a new f. But what does it mean in terms of, is there any way to interpret these models? So you might want to know what are the dominant eigenfunctions of the PDE, or does the PDE have symmetry, or does the solution satisfy some conservation laws, or are there any singularities that are developing? And the way that I'm going to do it through Green's functions allows for some more interpretability of the model once you've trained. Okay, so let's get into it. So Green's functions. So if you give me a elliptic, second order uniformly elliptic PDE in 3 dimensions, then there's a solution operator that's associated to it. And that solution operator is an integral operator that looks like this, which is parameterized, let's say, by a Green's function, this G. So this is the kernel of this integral operator. And if you give me an FJ, it maps the FJs to the UJs. So this is a representation through this integral operator for uniformly elliptic PDEs in 1, 2, and 3 dimensions. Okay, and so I'm going to try to recover this G as part of this solution operator. So this is what it looks like in 1D. They're very hard to visualize in higher dimensions, so I just do the 1D visualizations. So you give me a like Poisson with 0 boundary conditions in 1D, then this is the Green's function. This is the function that sits inside this integral that maps the right-hand side's f's to the solution's u. And you can see it's smooth everywhere apart from there. It's like a hat function. It's got a kink on the diagonal. You can also do this for Helmholtz. Here's the one for Helmholtz. It depends on this K. As I say, you give me a uniformly elliptic PDE and I can write down the Green's function associated to it. And in 2D, this is a 4-dimensional function. And in 3D, it's a 6-dimensional function. In 1D, it's 2-dimensional. Okay. And then after I've got this Green's function, I can tell you what we can glean from it, like what we can uncover about the underlying partial differential operator. This is kind of like the right inverse. You should think of it like the right inverse of the PDE operator. So this is kind of one of the punchlines of the talk, and I'm going to explain how you get to this kind of result and this algorithm. So let's just restrict ourselves to 3D uniformly elliptic PDEs, and I'll just keep the absolute simplest form so I can write everything down as explicitly as possible. This is the self-adjoint. This is a self-adjoint elliptic PDE. Then what we have here is a randomized algorithm where we know everything about it, which means if you give me an epsilon, which you say, okay, I want to learn this Green's function to within epsilon, I can tell you what input-output data to try, and how much you need, which is here, and what accuracy you get at the end if you run this algorithm. And this is a randomized algorithm, so it works with high probability. Okay, so you can see here that you're going to learn this, you're going to eventually recover this Green's function, which is the G tiddle is the recovered Green's function. G is the exact one that I don't know, I'm trying to find, to within about epsilon, and you need this many. Our algorithm requires you to use this many input-output pairs. So this is a lot. There's also this parameter gamma epsilon, which is actually a measure of the quality of these pairs. And I'm going to say more about that later, about what this gamma epsilon is. But you should think of it like this. If the Fs are really smooth, then I'm not going to be able to probe the high frequency components of the Green's function. Whereas if the Fs are very oscillatory, very high frequency, then that allows me to get deeper and probe the higher frequency contents of the Green's function. And this gamma epsilon is a measure of how much frequencies, how complicated these Fs are that you're trying. I'll say more about that later. Okay, and we're going to get ourselves to become fully rigorous and mathematically rigorous, we're going to have to use tools that move away from neural nets, because for neural nets you can't understand, it's very hard to understand training, fully understand training. So we're not going to have a neural net based approach, but it's going to motivate a neural net approach in my last part of the talk. So we're going to use randomized linear algebra, some low rank, which are properties of Green's functions, and some other properties of Green's functions. Okay. So let's get into it. So I'm first going to tell you the randomized SVD, which you may know, but I'm going to tell you it in a different way than you may think of it as. So if I have in my hands a symmetric low rank matrix, and you're allowed to give me vectors, and I'll give you back A times that vector. Okay, and your job is to discover what A I have in my pocket. How might you do that? How would you recover A from matrix vector products? Well, one algorithm is the randomized SVD. So what does the randomized SVD do to recover A? Well, first you select some inputs to try. And the randomized SVD chooses Gaussian random vectors. So here I've stacked them all up in columns. So there are K plus 5, let's say, vectors that you're going to try, and they're all random Gaussians, standard IID entries. Then you give them to me, and I return to you the matrix vector products. This is a vectorized way of saying that. I apply A to Y, and I get back all of them, the Z. So Z is trying to be a basis for the column space of A. Well, let's say it's a basis for the dominant part of the column space of A. Right, because it outputs from AY. So what do? You orthogonalize that basis, and then you project the column space. QQ transpose is a projection. you project the column space of A down, and you get a rank, in this case, K plus 5 matrix that you would hope approximates A. And the reason that the Science Review paper here is so popular is because they managed to prove rigorous theorems with constants, and we know it's all explicit. So this is the kind of guarantees that you get with very high probability. I've just put here, 0.01%. The AK that you recover from this randomized SVD is near best. So epsilon K here is the best you can ever do. That's an SVD calculation, which of course you don't want to do because you don't have access to A. You only have access to its matvex. AK can be constructed purely from matrix vector products, but yet A minus AK is near best. You've lost the small factor that depends on the rank that you're going for, this square root K. So within high probability, you're near best. And this is why we like it. It's not a Monte Carlo-like method. It's got very small variance. So if I plot the black line here is the absolute best you can do for a given matrix A, computed by the singular value decomposition. And the blue line is what this algorithm does to recover A. So you can see that it's nearly recovering the optimal rank K, best rank K approximation to A with only like O of K inputs. So this is a matrix recovery algorithm, if you like to say it that way. That's near optimal, right? With a near optimal number of matrix vector products, it's recovering the best rank K approximation, which is the best you can do. This doesn't just work for standard IID Gaussian vectors. This also works for many other types of random vectors. And here we reproved the randomized SVD when you have correlated inputs. So these are now, you're not going to supply me with random vectors, you're going to supply me with multivariable Gaussian vectors, where the entries of that vector are correlated to each other. Okay, and you can prove the same thing, essentially. There's a gamma K here, which is measuring how much correlation there is between the entries. So if there's a lot of correlation, then your vector is nearly constant. And therefore, you're not going to be able to probe all the different aspects of A. Whereas if you have nearly, the correlation matrix is close to the identity, then the vectors that you put in are close to being IID random. And this number here will be large and you'll do a good job. So depending on how much correlation you're allowing in your vectors dictates how near best you are. Okay, and this is just showing you that actually this can outperform the randomized SVD because you can bias the inputs in such a way that if I know something about A, and I can bias the inputs so I probe the parts that I don't know. So that's just an aside. But the reason that we need correlated Gaussian vectors to do Green's functions is because we can now have a continuous analog of the randomized SVD. So just to get us into that, first off, maybe we should just point out that functions have a singular value decomposition as well, just like matrices. In fact, this singular value decomposition for functions came before matrices. So in 1907, Schmidt wrote down a beautiful paper in German that was describing the singular value decomposition in all its glory, except he called it eigenvalues at that time. Only later did Erkach and Young in the 1930s pick it up. Well, they didn't know about Schmidt's full amount of Schmidt's work, but they wrote it down for matrices, and that got popular. But it existed for functions first. And this says that you can write down a singular value decomposition for a Green's function or for a function that's, okay, now there are potentially infinitely many terms in your singular value decomposition rather than a finite number. But it works the same. This U matrix here has orthonormal columns. This sigma matrix is diagonal with positive entries that are monotonically non-increasing. And this V transpose matrix here has got orthonormal rows. So it works the same. And many functions that you would think have very rapidly decaying singular values. So like here, this trigonometric function is actually rank 4. A rank 1 function is a function of x times a function of y. So it's like a column and a row. It's like an outer product with a column and a row. Most functions, like this array function here, is infinite rank, but they can be well approximated by low rank functions. Like this one's of infinite rank, but it can be approximated to within 16 digits by a rank 58 function. And that's because these singular values decay so fast. Or like here, this like kind of Runge function is infinite rank mathematically, but numerically it's only rank 33. Okay, so just that's the SVD, and that's what we mean by best, right? When you chop this series off after k terms, is the best rank k function to approximate a function, but you can find it using a continuous analog of the randomized SVD. So now instead of having matrix vector products, we have operator function products. And here is our operation function product. You give me f and I'll return to you this integral. So this is a continuous analog of a matrix vector product. And what is the randomized SVD for an integral operator? This is how we're going to find our solution operator, right? It's, you give me some random functions, so like y, and the continuous analog of a multivariable Gaussian distribution is a Gaussian process. Okay, so that's what generates a function now. If you sample these functions on a grid, you get a multivariable Gaussian distribution. Maybe these functions are very smooth, right? Maybe these functions that live inside this matrix here are very smooth, and then you won't be able to probe the high frequency content of G. Or maybe they get you want to make them a little bit more complicated, and then I can do a bit better, or you want to make them really random. But you can see here that these are continuous functions. And so by the fact that these functions are continuous, there's correlations between their values. And that's why we needed to extend the randomized SVD to allow for correlated inputs. So here we have a randomized SVD with correlated inputs, or random functions from a Gaussian process. But now you do the same thing. You plug those functions into the solution operator and you see the response. So this is like a matrix vector product, an operator function product. You get back these z's, these zi's. These are trying to be functions that span the dominant column space of this integral operator, the dominant part of the range of this integral operator. So you orthogonalize them, like let's say using Gram-Schmidt, and then you do the same thing. You try to project, or you project the column space of the function g onto that basis q. So this is the same procedure, except you have like correlated inputs in your SVD. And you can prove things about this algorithm, like it does a really good job. So now this algorithm here with k plus 5 inputs gets near best rank approximation. So with very high probability, this GK that you construct here will be very close to G in the Al2 norm, which is the continuous version of the Frobenius norm. And there's again this gamma K, which is telling you how rough or smooth these functions are that you put in, which is telling you how correlated the inputs are of the function f's that you're trying, or these y's. Now, this all works super well if your function is low rank or has rapidly decaying singular values, because then this eta k, which is the best rank k approximation, is tiny, and this gk will be close to g. The trouble with Green's functions, they don't have rapidly decaying singular values. This is because if you imagine that Poisson Green's function again, it has a discontinuity in its derivative along the diagonal. And this diagonal pattern is not aligned with the coordinate axes. And hurts your decay of your singular values. So Green's functions typically do not have rapidly decaying singular values, which means this eta k decays super slowly, which means this k would have to be huge if you wanted a good accuracy. So that this approach does not explain the success of neural nets right now. Instead, we're going to have to use some more properties that we know about Green's functions to try to accelerate this global randomized SVD technique that we're applying here. So, okay, this is just to say, what makes something low rank for a function? Well, smoothness makes it low rank. The smoother the function, the faster the singular values decay. So the reason that this Green's functions typically don't have rapidly decaying singular values is because they're not smooth globally. On the diagonal, they don't have much smoothness. Well, for some Green's functions, they explode on the diagonal, so they have no smoothness at all. And that hurts your decay rate of your singular values. So if only we can find parts of this Green's function that are very smooth, this will make the randomized SVD algorithm work really well. And there's a technique that's well established in numerical PDEs, which uses this low rank structure in a different way than globally and gets really good results for approximating Green's functions. And that is known as hierarchical low rank matrices. And the idea here is we know the Green's function as a global function is not low rank. So what we do is we start cutting it up into pieces in a hierarchical way. So here I'm trying to show you this hierarchy. When you're close to the diagonal, which is where all the non-smoothness happens in the function g, the domains you're taking are very, very small. As you move away from the diagonal, you take bigger and bigger domains, bigger and bigger chunks of your g. And you do this in such a way that the rank, or the numerical rank of the Green's function on each block, big or small, is about constant. So you should imagine all these green blocks, these green parts of the function, they all have about the same number of singular values above epsilon. Okay, so this is, when you're far away, you can take bigger blocks. When you're close to the diagonal where you get the trouble, you take small blocks. And these red blocks here are blocks that don't have any low rank structure. And that's because they nearly touch the diagonal, which is where the non-smoothness happens, right, of this thing. So here's how we construct an algorithm that's rigorous, that works at recovering this Green's function. You take your domain. Okay, I'm imagining here it's a square. If it's not a square, you enclose it into a square. I'm just doing the pictures in 1D, but it also works in any dimensions. So you cut it up into pieces. Let's say here I took 16 pieces, and anything away from the diagonal is low rank. And so you go away and you recover the green parts of the Green's function using the randomized singular value decomposition. The red parts you can't touch yet, because those red parts don't have rapidly decaying singular values. So you'll be wasting your operator function products, wasting your forcing terms if you try to use it right now to learn those diagonals. Then anything in red, you chop up again. You chop up you cut them all in half, right? Half in every dimension. The gray parts in level 3 here, you've already recovered at the previous level. But now you have new green blocks that are low rank, or at least numerically low rank, that you can recover using input-output data. So you do that, and then you go again. Anything red, you cut up again, you recover the green parts, and you keep peeling off these green parts as you squeeze up to the diagonal. Anything in gray has been recovered by the continuous analog of the randomized singular value decomposition. Okay, this is just to say that this all works in 3 dimensions too. But it's very hard to draw pictures because it really should be a 6-dimensional picture, because the Green's function is 6-dimensional. But Benbendorf and Hackbush in 2003 have completely analyzed this low rank structure that holds for all uniformly elliptic, all Green's functions associated to uniformly elliptic PDEs in 3 dimensions. And it's the same story. If you're away from the diagonal, you have low rank. So well-separated blocks have low rank interactions. Okay. And many people have used this already for matrices and recovering matrices. And we're doing it now to recover Green's functions, which are kind of the continuous analog of hierarchical matrices. So there's a problem. Maybe if you're really listening, you might think, what happens to that red region? Okay, you keep hierarchically cutting down, and eventually there's still on every level going to be a few red blocks that you can't currently recover because it doesn't have low rank. But it's also known that these Green's functions, they may blow up on the diagonal, like actually go to infinity, even though their 2 norm is bounded. But they don't go to infinity too fast, which means that as I squeeze down to this diagonal, the contribution that those little red regions make to the overall 2 norm of the Green's function gets smaller and smaller and smaller. And once the contribution gets so small, it's below epsilon, there's no point even recovering that part of the Green's function, because the Green's function is just got such a small 2 norm on those red regions. So at some point, we stop the process and replace our approximation by 0. The red regions, we just replace it by 0 and just say, that's a good enough approximation, we're done. So we learn these green regions until we get to a certain level, which we work out, and then you just set them to 0 because you have these kind of off-diagonal decay rates that we know. So this is how we get this algorithm. Okay, there are about, in 3 dimensions, there are about epsilon to the -6 green squares as you do this cutting. You need log 1 over epsilon levels, and each level requires about log cubed 1 over epsilon input-output data to learn. So each block. So this is where this comes from. This gamma epsilon is how rough your generator is for generating these input-output data. So that's that picture. If I get smooth functions and you only allow me smooth functions, then this gamma k will be small and you'll need tons of inputs and you won't be able to get good accuracy anyway. If the f's that you're allowing me to generate with this random Gaussian process are very rough, then this gamma epsilon will be very large and you'll be able to get very good approximation, and also with not too many input outputs, as many input outputs. Okay, so this is our theoretical algorithm that is guaranteed to work with high probability, mixing together a continuous analog of the randomized SVD, hierarchical low rank structure, and some off-diagonal decay. Just to say a little bit more about this quality of training data, because this is the kind of insight that we use when we now flick to neural nets, is this gamma k here, which is that quantity measuring the roughness of the input-output data. We know it's implicitly defined in the sense that I need you to tell me the PDE operator if you want me to figure out exactly what the gamma k is, but we know how to work it out, and it's basically saying, don't give me input output data that's orthogonal to the dominant part of my Green's function, because if you do that, I have no chance to learn the Green's function, because what comes in is not seeing the dominant part. However, if you let me probe the dominant part of your Green's function, then I can do a good job. And so this is what this is measuring. So it's just this kind of factor has to be always there. This is an intrinsic factor that's impossible to overcome, that you're going to have to know. The quality of your training data has to appear in any bounds that you would ever write down for any rigorous algorithm that recovers a Green's function. Okay. Now, what do we do in practice? Now we have tried obviously that hierarchical algorithm, and it works, and you get good approximation of the Green's functions. But we find that neural nets beat that algorithm within constants. So if our algorithm needs, if the hierarchical algorithm needs 500 input outputs to get the Green's function within 2 digits, then a neural net might only require 25. So there's, the neural nets seem to always beat that rigorous algorithm by constants. And something we're, I mean, that's an open question of like exactly why that's happening. Because now if I do neural nets, I'm not doing a fully rigorous approach. But yet it's beating the rigorous approach by constants. So this is maybe one of the reasons why people like to use deep learning techniques, is there are other good techniques out there that are rigorous, but the deep learning techniques seem to be beating those techniques by constant factors in the input output data. And something that's like an open question to try to figure out exactly why. So so we're going to use the understanding that we've got from the theoretical algorithm to develop a deep learning method, which will beat the other algorithm by constants. So in the hierarchical approach, we used random inputs drawn from Gaussian processes to probe our PDE. And that's what we're going to use here. We're going to have a covariance kernel, which I've just done in 2 dimensions here so you can visualize it. As you can see, it's close to the identity. It's close, like dominating the diagonal, which means it's going to generate lots of high frequency functions for me. And I'm going to stack them up here. I'm going to then put each one into this system and see the response. Right? So these are the Fs and these are the Us. And this is me collecting training data. I'm then going to write down, instead of trying to learn the Green's function, which is represented by a hierarchical low rank structure, I'm going to represent the Green's function by a neural net. So this is what the ngxy is. It's still trying to be the Green's function, but it's a neural net representation for it. These fj's are the random ones that I might try for the hierarchical algorithm as well. We typically extract out the boundary conditions to try to get the homogeneous part separately to try to make this guy more interpretable, but this is not that important. And you can see here we just have a loss function which depends on how well your solution operator is doing at matching the training data, fj and uj's, right? If you forget this homogeneous part. Okay, but there's a big problem when we tried this with standard neural nets. So like ReLU neural nets, they do not a very good job at learning these Green's functions. And why is that? That's because these Green's functions in 2 and 3 dimensions in particular blow up on the singularities. And it's very hard for a ReLU neural network to capture that blow up. So while 1D elliptic, they look they're not smooth on the diagonal, they're not differentiable across the diagonal, but otherwise they're continuous. In 2 dimensions, this is what the Green's function looks like. It blows up on the diagonal like a logarithm. And in 3D, it's even worse. It blows up like 1 over r, 1 over the distance to the diagonal. So how do you capture blow-ups? This is what this neural net's trying to capture. It's trying to capture these functions. How do you capture blow-ups in your function with ReLU? It has to put tons of pieces and they have to ramp up and get very steep to be able to even approximate this. And that's what the ReLU neural network is trying to do. But we know from an approximation theory point of view how to do better than ramp functions for functions that blow up. And okay, so this is a neural net, which I assume everyone knows. Ramp functions give you piecewise linear approximations, right? And smoother ones give you smooth, but they struggle with the diagonals, all of these types. But we do know techniques that allow us to do singularities. And these are known as composite rational functions. This goes back to the 1870s where they were doing neural nets, but they were doing neural nets for rational activation functions. So let me just explain that through this sine function, which is a function that jumps. Okay, so it's a little different than a blow up, but it's the same thing that's going on. Zolotarev was a student of Chebyshev, and he got asked by Chebyshev to repeat all Chebyshev's min-max calculations from polynomials to rationals. So rational functions are, of course, polynomial divided by polynomials. And so he managed to figure out through what is called an equi-oscillation theorem, which you get for rationals as well as polynomials, is that I can write down a best rational fit to this function that jumps, and it's this nasty function here. This is actually, I've done it deliberately. It's a very high degree, let's say, exponentially high degree in k. And it looks like it requires exponential number of parameters to parameterize this rational function. Well, that's not very good, right? If I have to take an exponential number of parameters to parameterize this function. But Lebedev clearly wrote down, I mean, Zolotayev seemed to potentially know that you can actually represent this rational function by a neural net, a rational neural net, where the width is 1 and the depth is k. And so Lebedev wrote down these AJs, BJs, and CJs so that this function here, which is the best fit to this sign, only involves 3k parameters instead of an exponential number of parameters. So here you can think of this as, okay, there's no linear part of this neural net, but the nonlinear activation functions are these type degree 3 with this x, degree 2, so 3, 2 type rational functions. And this does a really good job at capturing jumps. And actually, by the way, if you can approximate sine of x, like here, you can actually figure out that you can approximate ReLU as well. So anything these rational neural nets, or anything ReLU can do, rational neural nets can do too, because they can just average, they can just approximate sine x and then average between x sine x and x. So anything ReLU can do, rationals can do, but it's not vice versa. If you can do anything that rationals do, doesn't mean that ReLU can do it. I mean, ReLU can't capture jumps and blow-ups as well. And we proved in a paper that you can actually use this to show that rational neural nets, these are neural nets where the activation function is a type 3-2 rational, have better approximation power than ReLU neural nets. And that's because, I'll just describe this table here, that's because ReLU is really good at approximating piecewise linear functions, but not as good at approximating very smooth functions like polynomials, because they have to put their pieces somewhere. Whereas smoother activation functions, like polynomials, are not that good at approximating piecewise linear because they can't capture the jumps in the derivative. But they're very good at smooth things. It's been known since the 1800s, late 1800s, that rationals can do a better job at both simultaneously. So they can do a very good job at piecewise linear. How do they do it? They put their poles in the complex plane. These are the zeros of the denominator. And they squeeze up to the parts where there's kinks in the derivative. And that allows them to approximate piecewise linear functions better. But of course, they can also capture polynomials, because if I set the denominator to 1, then the top is a polynomial. And these composite rational functions have a very low number of parameters and are very high degree rationals. And so that's what we use. And some people have been showing that they do well for learning functions that jump and have singularities. So here is so we take our neural net and we have a look at what happens when we try different neural networks trying to recover this Green's function. So this is a Helmholtz equation. There's a singularity on the singularity derivative along the diagonal. Right, you can see that with the same size neural nets, so it's roughly the same number of parameters per neural net, the smooth activation functions and the piecewise linear do a worse job than the rational neural net. And this situation gets even worse as you go into 2 and 3 dimensions, because the Green's function blows up. So this is what we do. Instead of taking these neural nets like this, we replace them by rational neural nets, which can capture that blow up. I mean, this homogeneous one, you don't have to do rationals. It just makes it more of a universal, but this one is very important to do as a rational neural net. Okay. So now let me just show you. So we're now going to have those random inputs and train this neural net to approximate the Green's function. And then here I'm plotting the Green's function in the end. I'm going to do some low dimension examples so I can like visualize what happened. So here we've got Schrödinger's double well. There's a double well potential. And you can see that from the Green's function because there are two regions in the Green's function that are like turned on, excited by these double wells. And so this is telling you that, you know, things can get trapped in these double wells. What can you, by the way, what can you do with a Green's function once you have it? Well, just in the same way that for a matrix A, its inverse has the same eigenvalues but reciprocated, and it has the same eigenvectors as A, the Green's function, being the right inverse of the PDE, has eigenvalues that are reciprocated, and its eigenfunctions are the same. So from this Green's function, once we've learned it, we can, okay, this is us computing it from the PDE, from the operator, and we're computing the dominant, the low frequency eigenmodes of this operator. And here we're doing the same thing, but we're doing it from the Green's function. And I'm just showing you here these, often you see this with Schrödinger, where you're plotting the eigenmodes over the top of the double well. And you're seeing that they're the same, right? So you can, from a Green's function, you can glean the eigenstates that correspond to low frequencies, low frequency eigenmodes, for example. Other things you can do is see shocks as well. Like, well, here we didn't, here is just like a singularity that occurs in the variable coefficient. So when x is negative, this is just diffusion, just this term here. And you get this Poisson, you get basically the Poisson Green's function coming back, right? That's down here when x is negative. But when x is positive, this term is dominating and you see almost like transport. And you can see that here because the Green's function is 0 over here and then it's turned on corresponding to what you might see for transport. We can actually find this point where this variable coefficient has its singularity. Bearing in mind, you should imagine that we do not know what L of u is. We just see this Green's function. We can actually find out where this singularity is by looking at the poles of the rational neural net. So the rational neural net that's approximating this Green's function, how is it doing it? Well, whenever there's a singularity, it has to put lots of poles into the complex plane to capture that singularity. And so here we're looking at the poles of the neural net in the complex plane to find out where they pinch, and that's where the singularity is. So here you can see lots of poles, and you can see them lining up at z equals 0, x equals 0, just where this singularity is, right here, right? So you can see them lining up and trying to approximate this part here by lining up their poles, as they must, really, if they're going to do a good job at approximating this function. Okay. Now, everything I said doesn't just hold in 1D, it holds in 2 and 3, right? All this can be extended. And here I'm just showing you a two-dimensional problem. Here this is like Stokes flow in a lid-driven cavity, and there's Green's functions here. Now there are actually 4 Green's functions because u is a vector valued function. So it's got the velocity in x and the velocity in y. And the Green's functions are telling you how forcing in x gives you a response in the u's, right? And so here I'm just examining slices of this Green's function because it's 4-dimensional to see the response that I'm getting from forcing terms. And these are the learned ones. And you can see that means we can predict the velocity that you get for a different right-hand side. So these are the things you can do once you have Green's functions. And in some sense, there's a fully rigorous algorithm underpinning it that allows you to explain why you can do such a good job. But then neural nets happen to be very practical at finding them. So what can you learn once you've got a Green's function? You can learn symmetries. So if the Green's function is symmetric, the PDE is Salver joint. That's it. You can learn dominant eigenvalues because the eigenvalues of G reciprocated are the eigenvalues of the differential operator. You can look at these poles in the complex plane to figure out singularity locations that happen in the variable coefficients of the PDE, as well as getting those corresponding eigenfunctions. So I will just stop here, and hopefully I have 5 minutes or so for questions. So what do? We developed a fully rigorous probabilistic, like randomized algorithm for recovering Green's functions associated to uniformly elliptic PDEs. We can also do parabolic PDEs. Now we can do elliptic PDEs and parabolic PDEs in any dimensions. And it used this concept of the generalized singular value decomposition, which is allowing the randomized SVD to work with correlated inputs or random functions, as well as the structure of the Green's function. So hierarchical low rank structure, as well as some decay rates. And in the end, we were comparing it against deep learning approaches and finding that those deep learning approaches were beating this rigorous algorithm by constants. And if you would like to try the deep learning approach, or rational neural nets, then we have packages. And to try rational neural nets is like 5 or 6 lines in TensorFlow. So that just makes it easy to try out. So anyway, I'll stop here, and hopefully we can have a nice discussion.
Okay.